So sorry I was not more prepared. So my book is actually right here. So that's a good thing. Let me grab my book and let's look at 7, 3, 9, and 13. And then we will move on to 7, 6, because I know we did not get through all the examples for 7, 6. So probably good to go through a few more examples out of that as well. And any other questions you guys might have. Okay, 7, 3. Does it feel good to open up your book and be like halfway done with it? Okay, so da, 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 da. Sorry, I must be moving slow this morning. All right, let's find 7, 3. Okay, number 9. So this is square root of 9e to the 6th power. Is that this one? Couldn't find an example. Got it. Okay, so the thing to remember with e is that you're going to treat e just like you would treat a variable like x. So any of the rules that apply to what you can do to x or x squared or whatever apply to e. So even though we know e has an an approximate value, when we're using it in equations, we can just treat it like another variable. Like you don't have to sit there and think, okay, well, this is 2.7 whatever, and how does that change? We're just going to treat it like a variable. So what I mean by that is in your head, you could think of this as 9x to the 6th power squared. And whatever you're going to do to something to the x power is what you're going to do to something to the e power. So what I mean by that is, I think it was last chapter 6, maybe, we did a lot of radicals. We can break up the square root sign, right? We can do square root of 9, square root of x to the 6th. So the square root of 9 is 3. And the square root of x to the 6th is x to the 3rd. Now, if you can't quite remember how this would work out, remember the same thing as, let's see, we could also write this as x to the 6th to the 1/2 power, because square roots can be written as 1/2. And so then if you multiply 6 times 1/2, you get 3. All right, so it's 3x cubed. So then we're going to do the same thing over here. I'm going to do square root of 9, square root of e to the 6th. Square root of 9 is still 3. The square root of e to the 6th is the same as e to the 6th to the 1/2 power, or e to the 3rd power. So you can see how they look the same, right? It's just we treat it like a variable. So then number 11, would be 3e. Oh, 13. Okay. You got that one? You subtract the variables? All right, cool. Number 13 will be the cube root of 8e to the 9x power, right? So first of all, let's break it up into 2. So the cube root of 8 times the cube root of e to the 9x power, okay? And then we need to remember that, okay, I don't think the cube root of 8 is a thing, is it? Oh no, I think it is. Is it 2? 2 times 2? Yeah, it's 2. So the cube root of 8 is 2. And then the cube root of e to the 9x power, let's rewrite that in our other form because I think that's easier. So it's e to the 9x power to the 1/3 power. Remember, we can write the cube root as 1/3, the square root is 1/2. So now we're just going to multiply 9x times 1/3. So it's going to be 2 times e. 9x times 1/3 is just going to leave us with 3x. So that's how we would do 13. Does that make sense, Daniel? Cool. All right, so on to, unless anybody has any other questions in 7.3. All right, I don't see anything in the chat. So let's move on to 7.6. So let's do a couple examples from each section in 7.6. How does that sound? Okay, so the first block of problems is 3 through 11, right? And what we're doing is it says solve the equation, and these are all equations that have our variable is an exponent instead of it being in the equation. So in order to solve, we need to get our variable down. So let's do, anybody have preference? 9? Let's do number 9 maybe. Okay, so 9 is, I should write smaller, 36 to the 5x plus 2 power. Equals 1/6 to the 11 minus x power. Okay, so what we have here is we have an equation, right? But unfortunately, our equation, all the variables are in the exponents. So how do we solve things that are in the exponents, right? Well, what we have is we kind of want to look at these equations. These are kind of like a puzzle for this set of equations. If somehow we can force our bases to be equal to each other. So basically, if I have my base a, like, so if I have a to the x power equals a to the 3rd power, then I can say, oh, since my bases are the same, then my exponents equal each other. So I would say, oh, x equals 3. If I have, b to the x power equals a to the 3rd power, then I cannot automatically say x equals 3 because I have different bases. So if I can get the same base, then I can assume that my exponents equal each other. Okay, and I think I don't know if it's on your note sheet or not, but it is in your book on 515. It's the property of equality for exponential equations. So basically, I think it is in your notes. Basically, if you get your bases to be the same, then the exponents equal each other. So right now, what the problem is in number 9, is that our bases are not the same. One has a base of 36 and one has a base of 1/6. So they're not the same base. But if I can turn them into numbers with the same base, then I can just set the exponents equal to each other and I'm good to go. Yeah, that's the question. How does one force it, right? You got to kind of look at it. So what I notice immediately when I see this problem is that I know that 36 is 6 squared. Okay, and 1/6 is 6 to the -1 power. So I just kind of look at it and see the pattern. Like it's kind of interesting how number 11 is like 25 and 1/125. So they kind of both have a factor of 25 in common. So you're going to kind of try to look at those common roots and see what do they kind of have in common. Okay, so once you figure that out, then you can rewrite your equation and use both base 6. So we can say, okay, this side becomes 6 squared to the 5x plus 2 power. And this side, and all we're doing right now, we haven't solved anything, is we're just rewriting the way that 36 and 1 over 6 are written, right? We're rewriting them in exponential form. This is 11 minus x. So now, if I simplify my exponents, then I'm going to have two base 6s that equal to each other, and I can use that exponent rule. So what do I mean by simplifying the exponents? Well, if you remember, if you have like x to the 3 to the 4th power, you multiply your exponents together to get x to the 12th power. All right, so we're going to do the same thing here. We're going to do 6, and then it's going to be 2 times 5x plus 2. That's what it's raised to, 6 to the 2 times 5x plus 2 power equals 6. And then over here we have negative 1 times 11 minus x. So now what we have is we have a mess for the exponents, but our bases are the same, right? We both have a base of 6. So now we can kind of ignore the base of 6 and say, oh, well, that just means that this equals this. All right, so let me erase over here, give myself some room. I still don't know how to make paint have a bigger eraser. Dun, 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 dun. It's probably some trick you guys know. Share it with me. Okay, so now we know that since we have the same base, we can just set the exponents to each other. We can ignore the 6s, basically. Once we have ones that equal each other, we can ignore the 6. So we have the select under image. Oh, that's how I would do it, Daniel. Got it. Now to remember that. So 2 times 5x plus 2 equals negative 1. I have more room here. Okay, times 11 minus x. So now my favorite property, if you have me for Algebra 1, my distributive property, right? 2 times 5x, 10x plus 4 equals negative 11 plus x, all right? I'm going to subtract x from both sides, and I get 9x plus 4 equals negative 11. Subtract 4 from both sides, and I end up with 9x equals negative 15, or x equals negative 15 over 9. So hopefully I did that right. Let's double check. You guys should be checking me. Let's see. Oh yeah, negative 5 over 3. So simplify, right? Divide the top and the bottom by 3. Okay, so that's the whole concept for 3 through 11. You think you can use it? Cool. So the big idea is make the two bases the same, and then you can ignore the bases. Yeah. So I got to listen in class, right? As long as you make those two bases the same, you're good to go. Okay, so then we have numbers 13 through 23. So these are solving exponential equations, right? So the one thing that you're going to remember can't remember 4 days ago. All right, so the one thing you want to remember for this, the way that these are going to look different. So let's do number. I'm just thinking, sorry. Let's do number 21. So let me write it out here because I apparently can't write and talk at the time. 1/3 6 to the negative 4x plus 1 equals 6. This looks fun, right? All right, so why does this look different than the equation that we just did? What is different about it? Well, the big difference is in the other equation that we just did, they both had exponents, right? They both had exponents with variables in it. So if this was like, yep, still in 7-6, same section. It's like three different problem types in one section. So before, the first section would have had like an X up here, right? And then we would have had to figure out how to make the bases the same. But this kind of exponential problem, we're going to use a different strategy to solve it, okay? And the strategy that we're going to use is actually based off 7-5, based off of the power property. Yep. So Elijah, you're exactly right. First, we're going to use algebra to remove as much as possible. Love it. That's the best way to say it. So we're going to basically get as close to x by itself as we can. Okay. So the whole loaner property. So divide 1/3 to make it 2. Actually, Elijah, I would do the opposite. So I would kind of, so remember when you're taking equations apart, you kind of want to do opposite PEMDAS, not always exactly, but kind of the same way. So I would actually subtract 1 from both sides first, because then you don't have to deal with multiplying 3 times everything. That's just me. You could do it the other way. So I would subtract 1 from both sides to get 5. And that way, when you multiply both sides by 3 to get rid of 1/3, you just have a simpler way of doing it. So yeah. So 3 times 1/3 is going to cancel each other out. So you get 6 to the negative 4x. Total side note, if you would have chose to multiply by 3 first, you could have, but you just would have had to make sure that you multiply everything by 3. Okay, so this part up here is algebra that you've been doing a long time, right? That's your Algebra 1 and part of Algebra 2. So now we get to this equation, and it's like, huh, okay, my x is up in my exponent. How in the world do I get my x out of my exponent? Anybody remember from Monday? How can we use these fun things, logarithms, to get rid of exponents? Crickets on the, make it a log. There you go. So there's this weird logarithmic property called the power property, right? We talked about the properties of logarithmics. Yep, you do the change thingy. So the property is called the power property. So this is the power property. It's log base b of m to the n equals n times log base b of m. Okay, so basically the exponent, the n, right, in a logarithmic function can be written as, you can basically take an exponent out of the exponent position and change it into multiplication. So that's why it's really helpful, right? The question is, we have to take the logarithmic function. What do we do? Do we just do plain old log with base 10? Do we do the, I can't forget how Greta said it, the lateral nog? I can't even say it right. The natural log. What do we use? Well, it all has to do with what our, yeah, it all has to do with what our base is right here, right? Because if I take the log, let's say if I take the log base 10 of 6, another way to write that is what? 10 to the what power equals 6. And that's not cool. But if I take the log base 6, if I can write, log base 6 of 6, then really what we're looking at is the number 1. Okay, so what I mean by that is if I take the log base 6 of 6, I get 1. And anytime you can multiply by 1 in algebra, that's a good thing, right? So just follow me a little bit. So if I say, all right, my base is 6, so what I'm going to do is I'm going to say it's the log base 6 of 6 to the negative 4x power. And then if I take the log of one side, got to do it to the other side. Same as always, right? One side always equals the other side. Log base 6 of 15. Okay, I basically applied this logarithm to both sides. So now, let's move over here. Okay, first I'm going to use my power property rule, right? I get to take this exponent up here and move it to the front to multiply. So I've got negative 4x times log base 6 of 6 equals the log of base 6 of 15. Oh, it's getting really messy, sorry. Log base 6 of 15. It's supposed to be a 6. That's a mess. Okay, what did we just say the log base 6 of 6 is, though? A log base 6 of 6 is just 6 to what power equals 6? It's 1. So this whole log base 6 of 6 just becomes 1. So we're left over with negative 4x times 1, so we don't even have to write it, equals the log base 6 of 15. Then to solve for x, I just need to divide both sides by negative 4, right? And I'm left over with x equals the log base 6 of 15 divided by 4. Now that, I don't know what that is. I will be quite honest with you. So what do I need to do? I need to switch over to Desmos, right? Let's see here. Desmos. So we are going to need to use, it's going to be the log base 6 of 15. No, I don't even have an account, divided by negative 4. Oh, we ended up with something different, Elijah. Either I typed it wrong or it's possible. Did I type that right? Let's flip back over here to our messy paint. Log base 6 of 15 divided by negative 4. I think that's right. All right, so how can we check? I don't know, what does the book say? About negative 3.78. Is that what I had? I don't remember. Oh, yeah, that's what we got. So now if we do not have a back of the book, how can we check our work? So really, if you go back to that original equation before we did all this crazy stuff, we have 1/3 times 6. Oh yeah, that's one option. Plug it in, right? 6 to the negative 4, let's try that, times negative 0.3778. That was not right. It's up here in the exponent. Come on, why won't you let me type in the exponent? There we go. It really does not want me to type this in this exponent. There we go. Always important to make sure that you're typing your equation in right. Really? This is an exponent. There we go. Oh, it doesn't even like my equation. Sorry, I don't understand you. There we go. So really, really close. And if we keep going, let's add a couple more. Really want to get it close to 6. There we go. 7, 8, 9. So that's one option, is plug it in. I didn't even think of that. Thank you. Another option would be to graph it, right? I could say, oh, this is my x that I was trying to find. And I am trying to find, when does it equal 6? And that is right here at negative 0.378. Sorry. It's my algebra student back in the day. So the big thing is, this is the checking part, right? Do you understand how logarithmic functions are helpful in getting that exponent out? I don't know what that means, Elijah. They do computerized testing. What does that mean? All right, should we do another one from this section? Because the next section is easy. We can do one from that super quickly. All right, so let's do one from that just so I can make sure that you guys are comfortable with that. So 25 through 31 really could not get much easier. Okay, so it looks really complicated. It's going to take me longer to write out the equation than it actually is. So if I have number 29, okay, which is log base 3 of 18x plus 7 equals the log base 3 of 3x plus 38. Yep, still 7, 6. 3 different types of problems all in one section. Okay. Did I write that right? No, 38. It's important to write the right numbers when you copy your work. Okay. Still 7, 6, number 29, different set of sections. Okay. So this actually goes back to the first problem we did in 7, 6, where I said if you can get the bases the same, then you can set the exponents equal to each other. Well, this one is if you can get the logarithms the same, then you can set the logarithms equal to each other. Okay, so do I have 2 logarithms that are the same? Yeah, it's log 3 for both sides. Sorry for my crazy 3. Yeah, it's log 3 on both sides, right? This is the same as this. It's kind of like the same idea when we had the base of 6 on both sides. So as long as these two match up, then you can ignore them and go straight to, oh, okay, whatever they're taking the logarithm of, yeah, the 3 is crazy, equals each other. So we just say, oh, the logarithm of 3, we just ignore that because it's the same. And that means 18x plus 7 has to equal 3x plus 38. So as long as the logarithms are the same, you can just, yeah, the 3 was crazy, sorry. You can just set whatever they're taking a logarithm of equal to each other and then solve. You guys can do this, right? Subtract 7. Subtract 3x. I'm going to try to do it all in one. So 15x equals 31, or x equals 31 over 15. Which is about, it's going to be about 2.1, right? It's really close to 30 over 15. So those are easy peasy. And it's not like they're going to trick you. The biggest thing that you could get tricked on is they could say, oh, well, you could give different logs with different bases, and then you just can't use the rule. But in your book, they gave you all logarithms that matched. In 7.5, are we allowed to use calculators? Well, let me, so in 7.6, is this set of equations, this set of problems okay? You guys good with 7.6, these 25 through 31? Silence on the chat. Well, if you're not okay with that, just let me know. I think that little section's pretty good. Daniel asked if we're allowed to use calculators in 7.5. You can use your calculator, but really, when you go to expand the expression, your calculator is not really going to help you. You just have to kind of know those rules of logarithmic functions. I don't even remember what's assigned in 7.5. Yeah, if you have to use it for a calculation, that's fine. And they give you some of the values, right? I don't think there's many problems out of that. Okay, so if you guys are good, I think I would like to do one more from that middle section, which is the weird log section. Because I think that's the most interesting, and it's actually really useful to mathematicians, at least, to be able to take the exponent, you know, if you have a variable that's an exponent, and to pull it out of the exponent, that's actually really helpful. Yeah, you can use, yeah, Daniel, you can use a calculator for if you want to calculate something, but you're going to have to show, you know, show that you understand the rules too in your homework. Yep, show your work. All right, so do you guys want to see one more from that section? Anybody have a preference? 13 through 23? I know, is anybody still here? Bueller? All right, well, I'm going to do one more problem and then you guys can go if you want to. How's that sound? You're good with this section? All right, if you're good, you guys can go ahead and add out, but I don't mind doing another one from this section. You're good? Awesome. All right, well, if you're good, then feel free to go. And if not, if you want to see one more, I will do one more. How's that sound? And just sorry, before you go, I did send out an email. It has a recording for next week to watch. It's all graphing, so it actually works out pretty well. Yeah, so check that out when you get a chance next week, and make sure. And I won't be there, so enjoy your free hour for co-op. And I will see you next Monday. Daniel, Spanish and writing, so much fun. Thanks. Bye, Greta. Elijah, if you want to do another one from that section, if not, like I said, I'm good either way. Bye, guys. Bye, Caitlin. Bye, Greta. Bye, Mackenzie. You got it, Elijah? Awesome.